record and start a new one. So we're going to have a chapter 4 and a chapter 5 file. Hey, that's cool. I discovered something. All right, so now what do I want to do? I want to share a screen. And this should be chapter 5 that's open here. And the slideshow is it's about light. Okay, so okay, so here comes the slideshow. Okay, it's giving me the green outline, but you don't see it up there. Okay, that's fine, doesn't matter. So light and matter. So we're going to talk about light, and I already talked a little about it, that it covers a lot of different types of what we call electromagnetic radiation in different categories. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays are the 7 categories. And matter is atoms and stuff, protons, electrons, stuff. And then how do they interact? Okay, there's a beam of light coming in, and there's a what we call a glass prism. The light goes into it and it splits into the rainbow. So that white light has all the colors there. And why does it look white when all the colors are there? Why don't we? Well, because each wavelength of light is going to go into the eye and affect a part of the cells in the retina, and different chemical reactions for each one. There's 3 different types in the retina, so RGB, and signals go to the brain, and the brain synthesizes them and generates a sensation that we call white light. And here's the path. You want to look at this and get an idea of what it's about. What I'm seeing here is across the top are the waves, and so the waves are longer on the right end, so radio. Microwave is sort of a subset, and then infrared, visible, ultraviolet, X-ray, gamma rays. The waves get shorter. And here's a scale that measures the wavelength. The wavelength is from peak to peak, adjacent peak to peak, or is one way of doing that. So that gives you the size of the wave. And then they're giving you an example of something that is that size. So you have a football field on the far right, and you have a hydrogen atom, and we don't have much of anything to show for the other things because what's there? That's that small. Frequency. Okay, light has a particular speed, and it's characterized by wavelength and frequency, and each wavelength has matching frequency. Wavelength times frequency is the speed of light. So as the wavelength gets longer, the frequency gets shorter, smaller. As the wavelength gets shorter, the frequency gets larger. And so you have the scale for frequency, and then energy goes with frequency. The higher the frequency, the higher the energy. So gamma rays have very high frequency. They are very energetic, and anything to the left of visible light is destructive in some way. We're concerned with exposure to ultraviolet for skin cancer. With the ozone layer breaking down, it produces changes, not very deep changes, superficial on the skin. X-rays, they ionize atoms, and they can produce chemical changes that could be carcinogenic, producing cancer. Gamma rays, even more so, radioactive material, atomic radiations from like nuclear weapons testing. So energy is highest for each bundle of energy here. We call these things photons. And so photons have different lengths and different energies, and then sources of them. So, you got X-ray machines, light bulbs, people give off heat, and radio transmitters, and then out in space, all of these radiations are out in space. But what gets through the atmosphere? Visible light comes through the atmosphere without being altered at all. Radio waves, but not all radio waves come through. And so we can have radio telescopes on the Earth and nothing else. Infrared makes it down maybe on the very high mountains, you can get a pretty good infrared exposure for telescopes sensitive to that. But all the rest, you got to put your observatories up in space. So that's where a lot of the telescopes are. Okay, light is an electromagnetic wave. So we talk about wavelength, peak to peak, and here's a hand shaking a rope, and that produces this kind of wave, and it's called a transverse wave because of the type of vibration. And light does the same kind of vibrating. It does, but it vibrates not material stuff, it vibrates electric fields. And if you have an electron sitting around, that electron can be subjected to that wave and be caused to move. And so we have wavelength as the horizontal measurement in this picture. The vertical measurement is called amplitude, and you measure from the center line. The higher the amplitude, the more energy the wave has. So on a water wave, this has amplitude. When you go out swimming, you can see little waves on the surface of the water, very low amplitude. They have very little energy. You get a storm and you got a big gigantic swell of 20-foot waves. There's a lot of energy in those waves. Wavelength and frequency. So again, the idea is the shorter the wave is, the higher the frequency is. You can look at the numbers here. And I've got 1 centimeter, 30 gigahertz. Half a centimeter, 60 gigahertz, quarter of a centimeter, 120 gigahertz. They go together, and the formula is simple. It's the wavelength times the frequency equals the speed of light. And all these types of waves are all light, but each type has its own properties. And so light's a wave, but it also can be thought of, starting in the 20th century, early on, that light could be thought of as coming in little bundles, little particles, a bundle of energy that would be an all or none reaction. And so we call those things photons. And so a photon has a wavelength and a frequency. And these are just two different pictures, the photon picture and the wave picture. Science isn't in agreement on having a single picture. So light appears to act in two different ways. And the energy of the photon goes with the frequency. High frequency, high energy. There's a formula. And here's an energy formula. Energy is a number times the frequency. Thought question. What do you think? A, B, or C?
C. B.
Okay, higher energy means higher frequency. Yeah, but it doesn't mention frequency here. It mentions wavelength. Is the wavelength related to the frequency?
No.
Yeah, high frequency, small wavelength. So the higher the energy, the shorter the wavelength. So those three things all go together. They're not independent. Okay, what is matter? Now switching topics. They got a dot here and they say 10 million atoms could fit end to end. So atoms are smaller. And when you blow it up and you look at an atom, the usual pictures you see are like you got a little, some kind of a lumpy sun in the middle and little planets going around it. But that's not a true picture because these matter particles are fuzzier and more energy than solid matter. And so when you look at an atom, the atom's going to have this nucleus at the center, which here's our little lumpy sun with brown particles. The red ones are the positive protons and the gray ones are the neutrons that are neutral. And electrons go around the outside in orbit, except the electrons are not particles. They're more like waves that are going around. So for learning about atoms the first time, the solar system model is pretty good because it gives you an idea of sort of how it works. But then you mature, you learn more about the details, and it ain't that way at all. And so the nucleus is at the center, the electrons are all around the outside. And that's the universe, the way we have it. The terminology, how many protons do you have? Well, the 1 is the smallest number. Uranium has 92 of them. Lead has 82. And oxygen has 8. And so the periodic table in chemistry lays it all out. And the number of protons. So if you only have 1, you're hydrogen. If you have 2, you're helium. The mass number is add together the protons and the neutrons together. So there's always going to be, when the atoms are small, the number of neutrons is more or less equal to the number of protons. When you get way out there, like with uranium, the number of neutrons is way bigger. So uranium would have 92 protons, but it's going to have something like 140 or so neutrons. That's kind of how that goes. This is kind of showing you at the bottom the atomic numbers, how many protons do you have? And in a neutral atom, the number of electrons should equal the number of protons. 6 positives, 6 negatives in a carbon atom. Isotope. Well, it's possible to have the same number of protons, but different number of neutrons. So for example, helium, He, the most common variety is number 4, 2 protons, 2 neutrons. But you could have a nice stable helium with just 1 neutron. They call that helium-3. Very much a minority. A molecule is when you have 2 or more atoms bonded together, like H2O is a molecule, CO2. And so carbon has 3 isotopes that we find in nature. One of them you probably heard of, carbon-14. It's used for dating material. Yeah, it's good for archaeology because the decay rate for carbon-14 is fairly high, and it can take you back in time, measuring things about 60,000 years. You can't measure the rocks from the Earth because you need to use uranium or some other atoms breaking down. All right, now, how do light and matter interact? And here's a list, 4 ways. Emission. Matter can give off light. I see that happening in the ceiling back there with the fluorescent light. It's emitting up here on this TV screen. Absorption is when light falls on something and the light is taken up. The energy of the light falls in on something. So a black car sitting out in the sun on a hot day, it gets hot, doesn't it? So it absorbs, and that light energy becomes heat energy. You can't create or destroy the energy, but you can change what kind it is. Transmission. Okay, I see light out there on the road. It's coming from a car out there. It's coming through the glass of the window. And so it's passing through that glass, it changes its speed inside the glass and comes out the other side. That's transmission. I can't see what's on the other side of that wall because that wall is not transparent. The materials absorb the light on the other side. Similarly, our light is getting absorbed into that, and on the other side, they can't see us. So an object could be transparent or opaque. And then you have reflection. Okay, I can see the ceiling light there reflecting off the wall. I can see some light reflecting off this table. So this dark table, black things absorb very well. And so white reflects. That's why down here in Hawaii, you see a lot of white cars. I would bet, I haven't gone to Alaska to see, I would bet you wouldn't see too many white cars in Alaska. In the wintertime, they'd probably want to have black cars. So it absorbs the heat and it's a little warmer. And here's a movie screen. There's light being projected onto the screen. The screen is made to reflect, and people see, every person sees something that's a little bit different. When reflection happens, the angles have to be the same. And so it's the angle right at the point of where the light hits and bounces off. And that is, if you have a mirror, the light uniformly does that and you get an image that you can see. I don't see an image of myself in that wall, even though light's coming from me onto that wall. The light is reflected so much, we call it scattering. And here's a picture where you've got this red chair and it's winter. There's a green tree. The sun is shining on the green tree and the sunlight is coming in with all the colors of the rainbow. But the light that bounces off the tree is green. What happens to the red and the blue and the orange and all? They're absorbed. Yeah, they're absorbed. And so that's an interesting thing because chlorophyll is green and plants have chlorophyll, green leaves and all that. They reflect the green, but they're absorbing the red and the blue. And that's what's giving the chemical energy to make the plant tissue grow. Okay, and so now inside here, there's light reflecting off a mirror to the guy's eye. He has a green hat on. He's wearing a lot of blue, brown shoes. He's got a red chair. The light that's inside there hits the red chair. The light bulb has a different mix than the sun does, but even so, the blue and the green and all that's in that lamp light is absorbed into the chair, and red light is reflected off, and he sees a red chair. And so that's kind of how things work with light. Why is a rose red? Question time.
Because red is the only thing that bounces off of it.
Okay, the answers are up there though. Which answer would you pick?
The rose reflects red light.
You're picking D, and you are right. It's reflection. Okay, so this is pretty simple and primitive presentation for light, but these are the kind of the ground rules for it and how light interacts with matter. So we want to talk about the spectrum of light. Now, and this is kind of an example that we're going to work through over many slides. And a spectrum is a spread. When you see the rainbow spread out, that's a spectrum. And we have three types of spectrum listed here: continuous, emission, and absorption. I can see looking at this, the one where it's emission, I have spikes going up. That means there's more light of this color than there is in the surroundings. So there's extra light being added. Absorption, light is being subtracted from the pattern. And so I have notches down into here. And over here, what kind, where my arrow, no, you can't see my arrow and I don't have a pointer. The mountain is eaten, like something ate into it there on the right, on the left side of that mound. Is that an absorption or an emission spectrum there on the right side of the picture?
Emission.
That on the very right, directly below the letter S of spectrum on the right side.
Oh, the little flutter. Where, like, if it was a mountain, it would like come down.
Look at the letter S in spectrum and go straight down and you'll see that what looks like a chewed out area. Is that an absorption or an emission?
Absorption.
Absorption. It's just like the one further over to the left, right? And that means that there's a spectrum coming in. It shows me here a continuous spectrum that's labeled. And it looks like if I didn't have that absorption line spectrum in there, this would go straight across and bridge it, and it would be a smooth pattern. Absorption means that some of that light was taken away out of the beam that was coming through. And on the far left, emission, something's been added. Now, what we're looking at here, this is a spectrum of some body in the solar system. And we're going to be looking at clues to help us figure out what it is. We see that this is not all visible light. If you look at the very bottom, you've got blue, green, and red listed there. There's the yellow area. And further to the left, it says ultraviolet. And to the right, it says infrared. So this is a very mixed bag of spectrum. I've got a visible light spectrum here that I go up to the top here where it's over the word green, and suddenly the slope drops off suddenly. And it's like a ski slope going down. And I got the spikes out there in the ultraviolet. So we want to address and understand how to read that. And so here's the colors of the spectrum. And this curve, the button that's pushed at the top says the sun. So this is the light coming in from the sun. We can see that the sun has its peak of intensity at what color? Where is that graph under the spectrum highest? What color is that at?
Bluish green.
Yeah, green. And yellow is in there too. So those are the peak wavelengths coming in from the sun. The sun doesn't uniformly put out all the colors equally in strength. It puts out in the yellow and the green area. That's where the sunlight coming down in is at its peak. Astronauts see the sun, we see the sun as sort of yellowish. It's talked of as a yellow star, but when astronauts go up in space, they look at the sun looks white. What happens to the white sun coming down to where it's seen as yellow on the Earth? The light has to go through an atmosphere, so there's absorption. So the blue is scattered out and red is pulled out. And so we get the remnants down here. And here are three different types of spectrum. The three that we see these same words: continuous, emission line, and absorption line. And so let's look at the example here. The top banner here, the sun is shining, the light goes into the glass prism and it's broken up, and we have the rainbow of light. It's not broken in any way. There's no dark areas in the middle of it. The emission spectrum, here we have, it's not showing me the sun. This is a cloud before the light gets into the prism. So the light goes into the cloud and it comes out, and when we break it up, we're seeing these lines. And where are these lines coming from? Well, this is coming somewhere, there's a sun out of the picture, it's shining in on this cloud, and that sunlight is not going into our spectrometer to be picked up. Instead, the light's coming out of the cloud sidewise and into the prism, and we're looking at that, what's coming out of the cloud. And we see our spectrum is dark, and it has lines in it, and those lines are coming out. And it turns out those lines are connected to what kind of atom it is that's in there. Now, to put the two pictures together on the very bottom, you've got the sun shining into the cloud, and the light goes through the cloud and comes out, and then we get a spectrum, and I can't see. Can you see if there's any dark lines in that spectrum? I see the rainbow. I think I see a couple of dark lines, but it's so small it's hard to see. But the graph below it shows me the dips, the spikes downward, where some light has been absorbed out of that. So when the sun, the pure sunlight, continuous spectrum enters this cloud of gassy material, certain wavelengths are pulled out and they don't continue, but everything else goes through unchanged. And so when you look at that spectrum, you see the colors, but you're going to have dark lines here and there going through it. And each atom makes its own pattern of dark lines. So where we lost energy here. We lost some light energy because it was absorbed. But that light doesn't stay absorbed. The atoms absorbed it. They don't hold on to it forever, and then they let it go, and it comes out, and it's emitted. And it's emitted in all directions. It doesn't go back to the direction it was going in when it started. And that's why it's coming off to the side in the middle and giving us that emission spectrum. Put the emission and the absorption spectrum together, you got the continuous spectrum that you had before. And so here's your continuous spectrum, maybe a little better picture here. The incandescent light with the filament, that's glowing. That has a continuous spectrum. The LED bulbs, what kind of spectrum do they have? They're a little heavy on the blue, right? Yeah, so they're a different physics. They're not giving us a continuous spectrum like that. The emission spectrum, here's a better picture of it now. I can see a black background. I can see colored bands of light on it. Those are the lines. And those are coming from, it's showing me here a cloud of gas that is somehow stimulated from nearby sources. It needs the input of light to excite the gas, to absorb the types of light, and then the light, it will give it off in a different direction. We'll see the emission spectrum. And then the absorption spectrum, we're going to see black lines on a rainbow background. Okay, and that is going to be, here we have colored lines on a black background. And here we have black lines on a colored background. Isn't that interesting? That the two match up. They match up perfectly. So the whole process of emission and absorption are two sides of the same coin. Now, this is a spectrum. This is a spectrum of the sun. And it's put together in a square fashion like this because the slide couldn't hold the full spectrum. So they slice it up and they make it so like you can read left to right down the page. And you see a lot of black zones in it. There's a lot of absorption. The surface of the sun gives off the pure continuous spectrum. So this tells us that the sunlight leaving the sun the sun has an atmosphere around it. And the light has to go through that atmosphere and it undergoes some absorption. And it has to come through our atmosphere to get to the ground where we see it. So there's going to be some absorption there too. And you notice that some of the absorptions seem to be pretty weak and some are pretty strong, some are pretty wide. And these are chemical fingerprints. Now this diagram is called an energy diagram. It says at the bottom, energy levels of hydrogen. Hydrogen is the simplest atom to analyze. One electron, one proton, so simple. Hydrogen, so we could think of the electron orbiting inside the atom. But in fact, it can't orbit everywhere. It can only orbit at certain places, just like when you're at a staircase. You can stand on one step or the other step, but you can't stand in between steps. So these are like, they're coming from the center of the atom going out. There are plateaus, orbits call them, where an electron can be, but it can't be anywhere in between. Unlike the solar system, planets could be anywhere in between, but inside the atom, it's a different rules entirely. And so these represent the levels. So it's much easier to draw straight lines than to try to draw circles with these levels. So scientists like to do it this way. And so an electron, each one represents an orbit, and the electron can jump from one orbit to another. Planets don't jump from one orbit to another, luckily. That wouldn't be too good for us, right? Not at all. But here they're showing the electrons falling from higher levels, dropping to the level 1. Level 1 is the lowest level it can be. That's called the ground state. It can't drop any closer than that. Even though the electron's negative and the proton further down is positive, it can't get any closer than that. And so it stays orbiting. Higher energy is higher up. Lower energy is lower down. So when an electron drops from one level to another, is it absorbing or is it emitting light when it drops down, as in this picture? Yeah, it's emitting. It's losing energy when it falls. And so it has to give that up, and you can't create or destroy the energy. It's got to go somewhere. It becomes a photon of light of a certain wavelength or frequency. And so with hydrogen, anything falling down into the ground state, level 1, is considered to be part of a certain family of photons, a series. Falling into level 2, that would produce, this one would produce a lot of visible light. The level 2 ones, the ones that are dropping to the lowest state would produce a lot of ultraviolet. And you notice, if you think of this as like a staircase, the steps are not equal in size. That first step is the biggest step. And the steps shrink in size as you go up, and they're squashed together out there toward the top. And so it's possible to kick an electron from one level to another. It's even possible to kick the electron out of the atom. If you can give it enough energy to get to the top plus a little more, that electron has escaped. Okay, and so we're focusing in on the number 2 level, the ones that drop down, and at the bottom we have a spectrum, and this is given the name the Bomber series. Bomber is someone's name, and those were known because we see with visible light, so we see these. We can't see the ultraviolet or the infrared ones. And when the theory was proposed as to how this works, to prove it, you had to find, well, okay, if there's a Bomber series, is there one for the ultraviolet as well? And they found it, and it was exactly where it was predicted. Okay, so this is skip over that. And chemical fingerprints. So every type of atom, hydrogen just has 1 electron, helium has 2, uranium has 92. The more electrons you have, the more complicated it is and complex. And if it can fall down, it can fall up if it's given energy. If it falls down, it gives up a photon of light. If an external photon of light of exactly the right energy comes in and hits that electron, it can boost it up onto another level, but it has to be exactly the right amount. Okay, and these are animations that I don't think you can play them with the slides. Chemical fingerprints. Here across the top, you see helium. Sodium just has 2 yellow lines. We've seen those kind of yellow lights for street lights at some point in the past. Neon has a lot of lines packed at the red end. And so red becomes a very predominant type of light for neon. I think it was the first, it was a gas in a long tube, kind of like a fluorescent bulb. That was invented back in the 1870s or 1880s. And people learned that, oh, we can, making the glass bulbs, we can bend it, we can make letters, we can have electric signs in the windows. That hasn't gone away.
Wasn't tungsten one of the first ones to be used?
Tungsten, yeah, tungsten in the incandescent bulb, it was the filament.
Yeah.
And why was tungsten picked? The filaments get very hot. Tungsten has the highest melting point.
And then in a vacuum, it would burn up or whatever.
Yeah, and they put an inert gas in there so it can't burn. If you had put oxygen in there, what would be the point of making the bulb? Yeah, you know, that it would just flash. That would be it.
And in fact, it did. And I also remember, because I watched a documentary like a couple of years ago about like the whole process of creating the bulb. One of the first things they tried was cardboard, and it actually worked, but it only worked for a couple minutes.
Cardboard.
Yeah,
That's a filament?
I think so.
Wow. I didn't think cardboard conducted and would certainly, it's not going to burn if there's no oxygen.
Yeah.
So they pump in an inert gas like argon or something that doesn't chemically react with anything.
Exactly. And then, so the cardboard worked for a while, but it was pretty much just burning out really, really
Yeah.
fast. So then they tried other things. They tried tungsten and it turned out to work. So that's what we got.
Yeah, and that was Edison's strategy. He wasn't working off a theory. He was just said, I want something to be inside this bulb and not burn. And what can I use? He just kept trying things and he eventually found tungsten was the best. And so they used tungsten. Okay, so there are specialists who study spectroscopy and they get to recognize these lines and the patterns that they have. And so when you look at something coming in light from space, you can break up the light, you can see various lines, and you can identify elements. So we can know what elements are in the sun, what elements are in that star, and so on. And here again is the solar spectrum, which we commented on. Now back to these our little puzzle here. Which are the absorption lines? Which letters show us the absorption lines in this picture?
A, C, and D.
A is not absorption. A is spiking up above the curve. That's emission.
C through D.
C and D, not through D. This where that erosion is at C and D.
Was that?
The line was between C and D again. I remembered.
Yeah, I missed that grade. I was out that day when the teacher taught the alphabet. Okay, so one of the things to look at is, yes, we've got an emission, we've got a couple of absorptions, we have two peaks in this. Okay, there's two mounds, and one of them is in the visible range. There's yellow, and yellow is pretty much near the peak of this first one. And there's one way out in the infrared that's smaller. Those are clues as to what this might be. Okay, so there's your answers, C and D. Which letter labels the peak of infrared light?
C. Oh, for infrared.
Peak of infrared light.
D.
No, D was our answer for an absorption. And it's not at a peak either. What about E? It's in the infrared zone, right? It's way to the right of the visible light.
But isn't that on the part where it's sloping down?
Well, yeah, but I mean, come on. I suppose the true peak, if I could touch the peak, I'd be to the left of the letter E by a little bit.
Well, from my angle, it looks like it would be like right in between D and E, favoring D.
Yeah, it's kind of like between D and E favoring E, yeah. But we already used D, so we can't use that as an answer.
So by those rules.
Yeah, so, I mean, they didn't, this is sort of a loosey-goosey question. Which letter or letters labels the emission lines?
So that would be D.
No, D was our answer for absorption. Remember we said C and D were absorption? Where there's light coming in from a source onto an object, and we're getting light back and we're looking at it and we see that there's a subtraction that happened in two places. And the amount of those lights, those wavelengths is less. That's absorption. Something got absorbed out of the original light. Emission is something gets put into the light. Is that happening anywhere in this graph?
So would it be B?
No, B is a peak. B is not absorb. B is not emission. A is emission. Okay, there's extra light at certain wavelengths there, and so that shows up as peaks. So something is adding to the original light that we're getting, and some stuff is subtracted, and somehow we're having two peaks. Something's going on here. Okay, we still don't know the answer. We're going to go through this another time or two. How does light tell us temperature? We can tell the temperature of the sun by measuring the light. We can tell the temperature of stars in the sky by looking at their light. And, you know, we don't have to stick a thermometer into them. They're too far away. But the light carries that information.
Wait, so would the process of heat expose more photons because it's given off?
Yeah, the hotter it is, the brighter it is a general principle. Hotter stars tend to be larger too. And so every square foot of their surface is giving off more light. So they're showing you here, and you've probably done this at some time. If you've had a piece of metal, stick it into a fire, and as it heats up, it starts to glow and it becomes red hot. It's hot enough to be glowing red. And if you make it still hotter, it starts glowing kind of orangey, and maybe eventually it'll turn into glowing white. And so you say it's white hot. And so we correlate that with temperature. A fellow I know who used to work in welding said, you know, he could see a piece of hot metal glowing and he could tell you the temperature because he had just done so much welding and learned a lot of temperatures. What temperature matches what color? The stars in the sky, it doesn't look like it. They're just little dots of light. But if you could see them, there's a lot of colors up there. Red stars, blue stars. You don't have any green stars. You got red and yellow and orange, and you got blue, shades of blue.
Because they're not loud enough.
Why not? Well, no, green is in between yellow and blue. You start at red, that's the coolest temperature.
Oh, wait, is that because of the fuel that the stars use?
No, we're talking, the fuel is happening at the center of the star. We're talking about the temperature of the surface. What color is the surface? So it's cooler, it starts red, the star becomes orange and yellow, doesn't become green, and then it becomes blue. Why is green left out? And the answer, what?
Something's absorbing.
Now, the answer, we have to talk physiology. Change subject. By the time you get to hot enough to have it be green, well, when it's red, a red star, it's not going to have an even balance of colors. It's going to be heavy on the red and maybe almost no blue. And so the star is going to look red. It might have a little bit of green in there, but the red is going to swamp everything. You go to the other end, star is real hot and it's glowing blue. Well, there's some red and green and yellow mixed into that, but mostly it's blue. Yeah.
Would it also be because of like the way our eyes interpret?
That's the idea, physiology of it. Yes.
Yeah.
Because our brain is so wired that when the colors have a certain mix to them at the temperature of the sun, where green is the maximum, the brain says white. We don't say the sun is a green star. And there's no, for us, there's no green stars.
Or for like cat or something else.
Yeah, some other critter, some alien with a different eye, whatever. Yeah. So the answer is, completely in a different ball field for this. Okay, so everything emits thermal radiation. And of course, humans emit it, and that's it's behind one of the types of night vision, right? Where they pick up the infrared coming off. And the thermal radiation spectrum depends on only one thing, and that's the temperature. Doesn't matter what the material is made of. Temperature, that's it. Now let's talk the radiation. Here are some radiation curves. First of all, in this graph, we see a rainbow standing up straight here. That's the visible light. We look at the bottom of the scale, it's wavelength. So long wavelength is red. So red is on the right and blue is on the left. Ultraviolet is on the left, infrared is on the right. The vertical scale, what does it say here? It says relative intensity per square meter of surface. So if I take a certain amount of a square foot or whatever, square meter, and I look at the light coming off and what's the amount of red? What's the amount of blue? What's the amount of certain ultraviolet wavelength? That's what we're graphing vertically. So we see we have the three graphs here, four of them actually. There's one down there for humans, but let's look at the other three. There's a red one, a yellow one, and a blue one. The blue one is 15,000 Kelvin star. That's hot. Our sun is about 6,000. So this is a very hot star. And hot stars emit more of everything. If we look at, let's look at red light. On the blue curve, it crosses into the red light very high up. The yellow crosses in a little lower and the red crosses in lower still. The hotter the star is, the more of everything it makes. So you don't have those curves crossing each other with one going under the other when it was above. They nest one inside the other. If I looking at the visible part, let's look at the sun, 5,800 Kelvin. And the sun, the top of the sun's curve is in the visible. And it's almost flat going across. So that means the sun is more or less giving equal amounts of all the colors, but a little bit more toward the center, gets a higher dose of the yellow and the green. The hot star, you look at where it crosses the visible, it's slanting upwards. Blue is a lot higher than is yellow or red. So heavy on the blue. You look at the red curve, it's slanting the other way. Heavy on the red, slanting down toward the blue. The scale is not a linear scale on the far left. That's called a logarithmic scale. So that means you make this kind of scale to cut the exaggeration of the graph so that it makes sense. The area under the graph is the type of energy. So our blue curve has a lot of area under the left side of it, of the blue. And that represents the amount of ultraviolet it's cranking out. When I look on the right side, I see kind of a triangle with that blue as the hypotenuse, and that represents the infrared that it's putting out. So the blue star is putting out as much ultraviolet, maybe more than the infrared. Probably you don't want to live on a planet in that solar system because your suntan, you get skin cancer instantly with that kind of exposure.
So could it also give off like gamma?
No, gamma strictly comes from the nucleus. It doesn't come from the electron orbits jumping. X-rays come from the electron orbits. Probably does give off some X-ray. But if you have an atmosphere, the X-ray can't get through it. Our sun gives off X-ray. We don't get solar X-rays on the surface.
But it doesn't our atmosphere also blocks some of the infrared?
Yeah, it does. It does. It does block some infrared, especially, where you might have water vapor. Infrared doesn't get through our atmosphere too easily. But we do have infrared observatories, and those are up on big mountain like Mauna Kea over on the Big Island, where it goes up like 4,000, is it 4,000 feet? It's up there quite a ways. No, 14,000 feet is the top of Mauna Kea, where the telescopes are. Up there, yeah, you can't get all the infrared spectrum, but you can get a lot of it. Down on the surface, you pretty much get almost nothing. So this is the kind of pattern to think of. And this would be a good chart to mark somewhere. And it says hotter objects emit more light at all frequencies. And it says per unit area, that you're talking like a single square foot. If you're going to compare a single square foot on all these stars, you're going to find that the hot star is giving off more light at every frequency compared to the other one. And hotter objects emit photons with a higher average energy. That means that if I'm looking at the red curve, it's coming down on the left side and it hits the axis on the bottom. Yeah. And there's nothing to the left of it. But the blue goes past that point and goes further to the left. So the blue star is putting out photons that almost none of them are coming out of the red star. And the yellow star is kind of in the middle. And then you have the human. Now, humans have a very low temperature compared to stars. On a Kelvin scale, our temperature, body temperature, is 310 Kelvin. Okay, that's about 98.6 Fahrenheit. It's 37 Celsius. It's 337 plus 273 gives you the 310. And what is our curve like? We do radiate. Are we emitting visible light? In a dark room, I don't think I can see any of you. You don't glow. But if I had infrared eyes or that type of night vision, I'd pick you up pretty clearly. And so we're not giving off any visible, we're giving off some infrared that's way out there and not very much of it. Okay, now Wien's law. What is Wien's law saying? Wien's law is saying about the temperature. Let's back up. This graph doesn't tell me anything here. Let's see, here's how I back up. I click this. Wien's law is looking for the peak, the high point on any temperature curve. And Wien's law says that if we can measure the light coming in from a star, and we can figure out where the top point is on that spectrum, we have a formula to get the temperature. So we won't go into where that formula came from, but Wien came up with it, and we call it Wien's law. So the light carries information about temperature. Which is hottest? Blue. Blue is the hottest. And this is backwards. We think of blue as cold, red is hot, don't we? Fire is red and ice is blue. But not in astronomy, not up there. Everything's, you got to switch gears when you're studying this and taking tests on it. Blue stars are hottest. Why don't we glow in the dark? B is right. We're only emitting infrared, and that is, we don't have sensors in our eyes to see infrared. Now, this is an actual spectrum. So now we want to learn about this object. Now we learned a few things. We learned about there are some absorption sections, there's emission sections, there's continuous sections. Okay, so now they're going to comment on this left side. That's reflected light because we're looking at a surface that is receiving input, and the input is bouncing back to us, and we're noticing, oh, something's absorbed, something's emitted. it's a continuous spectrum, but it kind of coming in from the right up to that peak, it suddenly drops off. Shouldn't it be a smoother curve? It sort of suddenly drops. So these are the colors that are coming back. We're seeing red coming back. We're seeing yellow coming back at the peak. We're seeing some green, but the blue looks like it's had a gigantic bite taken out of it. Okay, what's going on there? This would have to be sunlight in the solar system of all colors coming in, hitting something. And what light is coming back mostly to us from it?
What we're seeing now.
Yeah. Yeah, this is what we're seeing now coming back at us. And just focus in on where the visible spectrum is below, and it's labeled blue, green, red.
Wouldn't it be blue?
Well, it looks like we're seeing what kind of light is coming back mostly to us? Well, yellow's highest, but the red end is coming back. It looks almost uninterrupted. It's probably an object that's red. And the blue in the sunlight has been taken out of it. So think about the red chair in that room that we looked at. All the colors are falling on it, but only the red is coming off. So it's absorbing. And it's not absorbing yellow. The yellow peak looks like it's a natural peak that's up there. So whatever it is we're looking at, it's the surface color is kind of not very much on the blue end, and it's more on the red end. That's a clue. The object says at the bottom, the object must look red. Okay, so that's sun's radiation. Now this down here, this is out in the infrared. This has to be thermal radiation, the one to peak on the far right. And you wouldn't know this from the caption at the bottom. You would probably not be able to say 225 Kelvin. I think it's 225 Kelvin peak, right? You'd need some instrumentation to measure that out. But it's way out there in the infrared, so it can't be too terribly hot. So, and 225 Kelvin is how much, what temperature level, Celsius or Fahrenheit, do you think? 273 is 0 degrees Celsius. Yeah, it's down there, it's cold, but not too cold. It's not absolute zero, but it's cold. It's cold and it's red, reddish color. What do you think it might be? Well, let's see if we have more clues, because they're giving us the clues. We couldn't possibly at our level of education here, just taking astronomy the first time, know all this stuff. The absorptions, it's saying this is carbon dioxide that does these particular absorptions. And so that's going to be coming not from the surface, that's going to be coming from the atmosphere. It's obviously it's a body in space that would have to have an atmosphere that would be kind of cold and red. What could that be? Well, let's move on and look at the other one. In the ultraviolet, we've got emission lines. And so those would tend to come not from the surface. Those would tend to come from the atmosphere. When sunlight's coming into the atmosphere, and the atmosphere would have to be a hotter temperature, generating ultraviolet. And why would the upper atmosphere be hotter than the lower atmosphere? Maybe because it's nearer to the sun and it's picking up X-rays from the sun. the X-rays get absorbed in the higher part of the atmosphere. That makes the atoms and molecules move faster. And that means higher temperature.
So when we go back, the CO2 is being absorbed by the atmosphere,
Yeah,
which is why we're seeing red. Is that what this is?
these are all separate phenomenon. There's stuff happening where there's ultraviolet being emitted, and you don't get ultraviolet being emitted unless you're putting ultraviolet in
Right.
or X-rays in. So that has to be higher up and away, not down at the bottom of the atmosphere, because your X-rays and UV won't be getting through to do that. It's got to happen at the top.
We're
Now-
supposed to be able to figure out what this object is.
Yeah.
So,
The hint is it's in the solar system, and this is sunlight shining on it. And this is what we pick up coming back off of it. So just like the chair in the room, the lamp was given off its own spectrum, and that hits the chair, red comes off. Out the green tree outside, sunlight comes in with a different spectrum, hits that tree, red and blue get absorbed, green comes off.
okay, so we're seeing red.
We're seeing mostly red. It's not pure red because that curve goes up and then it takes a steep dive, the one on the left.
Right. Okay. This is a celestial body in our solar system.
Yeah.
It's a planet.
That's a good guess. Not too many other things out there.
Right.
Comets,
Comets,
asteroids.
rocks, whatever.
Yeah,
Okay.
with atmospheres, comets don't have atmospheres, neither do asteroids.
I'm gonna Jupiter emits like an orangish brown.
Yeah. Is Mars red?
Yes.
Whoa. Does Mars have carbon dioxide?
Yes.
The atmosphere is 95% carbon dioxide. It's a very thin atmosphere, but it's CO2. Yeah. So there's only so many planets in the solar system that you pick, so. And Mars, we know a lot about it. Okay, now light tells us how fast something is moving. So you think of Doppler radar, right? How does a radar detector work looking at a car that's coming down the highway?
This is off.
The radar is emitted at a certain wavelength, and off it goes, and it hits the car, and it reflects and comes back, but the car is moving. And so what that does, as the radar ray was being turned around to come back, is the wave gets squeezed shorter a little bit. So it comes back with a slightly different wavelength, and the detector picks it up and says, this ain't the same wavelength I sent out, it's different by this much. Quick, calculate. You're doing 80 miles an hour. Something like that.
It's Doppler shift.
Yeah, so there's a Doppler shift. Okay, well, the same thing sort of happens if you hear this with a siren coming down the street. Okay, so as you hear it, the Doppler shift, it gets louder coming towards you. That has nothing to do with it. Of course it gets louder, it's closer. But the siren standing still emits a certain tone. And it's not a pure tone, it's a mixture. But as it's coming towards you, all those sound waves get compressed. Because once the sound takes off, it's going at the speed of sound. It has nothing to do with that vehicle anymore. But the back end of the wave is compressed toward the front end of the wave. So it's a shorter wavelength. That changes the frequency. That changes what you hear. So as it's coming toward you, squashing the wave, you hear a higher pitch of sound.
It's that apparent shift of frequency.
Yeah. And that's coming towards you. The instant it passes you, the wave is stretched. And that's where you listen for the Doppler effect when it's passing you, that there's a sudden change in frequency. And of course, it fades away into the distance, but that's not the Doppler effect. So the same thing happens with light, except the speed of light is so fast that, if you you went, cop pulls you over going through a red light. Says you went through a red light. I said, it looked green to me. And he said, oh, then you were speeding. Because if it was a red light and it looked green to you, you must have been going real fast to compress that light wave to where it looked green. So that's the thing with Doppler. And so the picture on the far left, we've got a train, I guess, emitting a siren. It's not moving. So where you stand on the front, you stand on the back, the sound is precisely exactly the same. If you're the same distance, same loudness, but the pitch that you hear. Now, if it's moving, it crushes the waves in front of it. It squashes them and compresses them, makes them shorter wavelengths, which means higher frequency. And so that sound is a higher pitch. On the back end, it's emitting the same sound, but it's moving. And so the wave gets stretched out. And so that is lower frequency. And this happens with light. But not enough to change the traffic light that you're moving towards it. Whatever speed I'm going towards the traffic light, I've never seen a red one turn green or even yellow.
Wait, you've never gone 99% speed of light?
No, the cars I buy, no, I haven't found one that does that yet.
Keyword there yet.
Yeah. And what's this last one? Light source. So you do this with light as well, but the speed of light is so big that the Doppler effect with light is not noticeable. And anyway, if you have a mix of wavelengths, that makes it really hard to see. You have to have a pure individual tone. The Doppler effect wasn't discovered until about the 1820s. And it was discovered when humans began to be able to travel real fast, like railroads were invented. That was faster than a horse and buggy. And these, they have horns and whistles on it, so the sound was different. So the guy who discovered it, Doppler, he had an experiment. He had a flatbed car that the train would tow, and he had an orchestra sit on that flatbed car and all play the same exact note. So he had a single frequency. And he had them coming towards him, he had them going away from him. He was able to determine the frequency of the sound change.
You know that people were afraid of trains at first because they thought that they would go so fast.
Yeah.
It started out like when they first came out, it was around like 30 miles an hour, which isn't fast to us now, but they thought that they would go so fast that they would like get crushed behind from the momentum of the train going forward.
Yeah. It was brand new. It was nothing like it. Horse and buggy didn't do that sort of thing. Okay, so that's the Doppler effect. And these are animations for the Doppler effect. We can skip through them. And this is an example of the shift. So let's see, stationary is at the top. Here's, I guess, the hydrogen spectrum with the red, green, and blue. And I think there's one more line here. It's hard to see on the left. If it's moving away from you, all those lines shift position. And you notice the green one is sort of taken on a yellowish tone, because that's where it is in a spectrum. Its wavelength has been compressed, stretched. What's going on here? If it's moving away, it stretches it out. So yeah, so the green stretches, becomes yellow. Going away faster, it moves even further. And so the instruments they have can tell where the wavelength, the lines are supposed to be and where they are. We can get a reading, how much change was there. We can calculate speed knowing that. And if it goes the other direction, you notice that the line color changes. The line is still the line, but why is the color changing? The wavelength has changed and your eye sees that particular color with that wavelength. Okay, and so this just tells us that. But now the Doppler is only towards you or away from you. Let's say you're working, you're on traffic detail, you got a radar detector, you're aiming down the avenue to see who's speeding. And so you can, whether they're coming towards you or away from you or on either side, you can get their speeds because you're right in line with them. Now there's an intersection down there and someone shoots across at 120 miles an hour. And your radar gun catches it. What is your reading on the radar gun?
I didn't hear all the numbers, I'm sorry.
What?
I didn't hear all the numbers.
There's only one number, 120 miles an hour. This car shoots across the intersection while you've got the radar gun on and you got your readout right in front of you.
If you're at 90 degrees to it, it would give it the actual speed of the car.
No, 0.
Yeah, they can't.
It's only line of sight. Doppler only works on the line of sight. Across it, you can't measure anything with Doppler.
That's why they have to always be head on to.
Yeah. And if it's at an angle, you get a fraction of it.
Yeah.
I play games with that. I see the speed by the side of the road. This is your speed. Well, there's a little radar gun in there bouncing. And so I noticed, I maintain a steady speed, but I'll be over to the lane over here and it's reading my true velocity. But the more I get here, the further off it starts getting because it's only catching a component.
That's why you really know radar. You can talk your way out of.
Yeah. Yeah, gone are the days when, the judge would take the radar gun outside to see how fast the church steeple was moving. It was going 25 miles an hour. Yeah, we'll throw that case out of court. Okay, here's a thought question for you. In the lab, the line is at measures 500.7. Same line coming in from a star, 502.8. Tell me something about the star.
Okay, it's moving away.
The line is getting longer. Regardless of the numbers, the wavelength's getting longer. That's a sign of redshift. They call it redshift, stretching out, that the line moves on the spectrum toward the red end. Doesn't matter what the color of the line is. Even if it's ultraviolet, it doesn't have a color. If it's stretching out, they call it redshift. So it's moving away from you. Okay, measuring it. We're going to go through this pretty quick. How are we doing on time?
8:36.
Oh, good. This clock here says 8:42, but 20 minutes. And I've only got 30 slides to go, and a lot of them are useless. Okay, what have we learned? Well, that's what we learned. How does light tell us the temperature? So we look for the peak of that spectrum. Speed. Okay, here it mentions redshift and blue shift. Redshift is when things are moving away from you. Blue shift is when they're coming towards you. The thing with the very far away galaxies out there in space, they're all doing redshift. They're all moving away from us. Okay, now instrumentation, telescopes. We're not going to get deep into telescopes. Galileo he didn't invent the telescope. Someone else did, but he learned about it. And he was smart enough to design a telescope. He said, we need 2 lenses, separate them. Okay, he can grind the glass and make lenses. And so, but visible light was all they had to look at the sky. It was only in the 1930s that it was discovered radio waves come in from the sky, and that invented, the big dishes for radio telescopes. And everything else has to be up there in space. So why do we put telescopes into space? Well, 2 reasons. If we're trying to look at X-rays or infrared or ultraviolet, it's the only place to do it is up there. But also, if you're using visible light, the atmosphere blurs things. although we've overcome that with this technique of active, they shoot a laser beam up and it measures the atmosphere and reflects back, and then computers adjust the telescope in real time so they can improve the image, and that gets to be almost Hubble quality. Okay, so a telescope is thought of as a light bucket. It's something you put out there into which you collect light. So they're bigger than our eyes are, so they have more area, so they collect more light. They can see more detail, and we call that resolution, angular resolution. So if you see a car far, far in the distance and it's got its headlights on at night, can you tell that there's two bulbs there, or does it just look like one? Probably just looks like one. At that distance, our eye can't resolve two separate objects because they look like they're so close together and they blur together. But as that car approaches us, we start to pick up two separate light sources. And that's resolution. Resolution from a satellite looking down on a planetary surface like Mars. We can see big craters. We can't really see small craters very well. We can't see boulders on the ground. The resolution is not high enough. Telescopes can detect light that's invisible to our eyes. So different designs for these things. Bigger is better. So these two telescopes here are on Mauna Kea on the Big Island. They're called the Keck telescopes. They are 10-meter telescopes. They want to put a 30-meter telescope up there. That won't be the biggest. Chile is building one. It'll be 37 meters if they get it finished. They're not having the issues in Chile with building it that they're having here on Hawaii. So the bigger it is, the more light you collect. And that lets you see things that are dimmer and further away. Of course, the time you expose is important too. So more area and leave it open longer on that object, you can pick up very faint objects out there. And you're looking down in here on the mirror of the telescope. I think there's a human standing in there in red to give you an idea of size. And I can't quite pick out the detail here. Let's see if this is better. The way those telescopes are made, yes, I can see from the outside, I have a hexagonal shape. It's kind of a jagged shape around the perimeter of that. And basically, it's a bunch of hexagons that are put together. Each one is a mirror. And those mirrors are individually controlled. So they can have they're made of glass and they're coated with aluminum, I think. And the light comes in and it reflects from them to a collecting area that's hovering above it in the center. And this active optics that they use, they'll send a laser beam up into the sky near where they want to look. And they'll be measuring with another telescope what that light is doing, how it's being shifted by the air, because the air can be turbulent. It's usually very, very calm and smooth on Mauna Kea, more than any place else in the world. But their turbulence happens. And when it does happen, it refracts the light. And so why do stars twinkle when you look at them? Stars don't twinkle. It's the atmosphere. That's the light's coming from the star. The star isn't twinkling, but the light comes in and then it has to bend this way and that because the density is changing because the winds are blowing. And that makes the star shift and we get that twinkling effect. And so this adaptive optics feeds into a computer, and the computer very quickly adjusts these, is calculated to adjust each of these hexagons, bend them ever so slightly to shift the light that's reflecting, and that improves the image. It's pretty remarkable. So bigger is better. Angular resolution, this would be a car coming towards us, but we can't play that thing. Smaller is better for angular resolution. We want to be able to see small things for detail. The basic telescope design, there's two kinds. There's refractors and there's reflectors. The refractor is the telescope that you might have had as a kid, or you're a pirate and you're looking through two lenses. It's glass lens here and a glass lens here. One's at the object and one's at the eyepiece. And this is a 1 meter long telescope. Yeah, it looks like it's probably 1 meter. It's a refractor. The light goes straight through the lenses and it comes out and you focus it down there. And so you can see it. Originally, people would look through telescopes. Eventually, they got to where they could attach a camera to it, take pictures. And that was a big advance. A mirror telescope, like the Keck telescopes, the light comes in, hits a concave set of mirrors or a single mirror, which then reflects the light back towards a point. And that point, that light that's being refracted back up the tube, two things can happen. One is it can be reflected again back down the way it came, except it's more concentrated and it goes out through a hole in the bottom where you can be looking or having a camera, or it can be reflected to the side and come out the side of the telescope. And if you're going to be buying a reflector telescope, that'd be one kind of design. You have a big cylinder of a telescope like this, lights coming in here, mirrors down here, reflects back. Then there's a surface, the light hits it here, it comes out. So you're just standing next to it, looking into this cylinder and seeing what's in the sky. And so this is Gemini North, that's Big Island. And you can only build a gigantic glass lens so big. That's why they don't, the 30-meter telescope is not going to be a glass lens. It's going to be a lot of mirrors. Glass sags with gravity. Glass, they say, they describe it as a supercooled liquid, that glass flows. And they found this out, interestingly. Back in the Middle Ages, they'd make, in Europe, they'd make the stained glass windows for the gigantic cathedrals they were building. And over in Venice was one of the big places where they'd make glass windows. They'd make the colored stained glass. And so they'd liquefy it and they'd spill it out on a smooth metal surface, kind of like this table. And it would spread, it would be equal thickness everywhere. It would cool and solidify. And it would be glass, you'd have glass, and you could cut it. And however they brought it to where Paris or wherever they're building the cathedral, it got there somehow, probably cut up a little bit. The artist may have wanted it cut while it's there on the table and then label the pieces and bring them all up. And they mount them up in the windows. So now the glass was horizontal and it was equal thickness everywhere. You cut the glass and you put it up, now it's all vertical. Okay, fast forward from 1200 when they built that cathedral to 1900. 700 years later, they're fixing the windows, they take out some pieces, and someone's interested, and they measure the top, the thickness at the top, they measure the thickness at the bottom, it's thicker at the bottom. What happened? Over time, the glass slowly flowed downward. And it will do that under the action of gravity. Now, if you try to make a big, gigantic lens, 10 feet across, 50 feet across, it ain't going to work because it'll be optically perfect. You make it smooth, lens shape, hang it up there, it's going to sag in the middle. There goes your good imagery. I think the Palomar telescope around LA, or is it San Diego? It's down there in California. That was the biggest telescope, went up, I think, 1940s. And then the Soviet Union tried to outdo the United States. We're better than you, we're going to make it even bigger. They made it bigger and the thing sagged. It was a dud. Should have figured that out. Okay, so yeah, these are Keck 1 and 2 on Mauna Kea, and this is Mauna Kea. I was up there about a few weeks ago. Kind of remarkable, low oxygen level. If you go up there, bring a lot of water to drink. That helps you a lot. And all these places do have oxygen for those who need it. So you see people going around with the hoses, like in a hospital. But nothing's growing up there. It's kind of,
Is there on Haleakala over Maui? Is there something over there?
yeah, there is. It's a solar observatory.
Okay, that's-
It's not as high up and
Yeah.
10,000 feet or something, and you don't need to worry about oxygen there.
When I was up there, I did get like a little bit like air sick.
Yeah, yeah,
But I was wondering what that was. Okay, solar observatory?
it's a solar, yeah.
Okay.
But if you go there again, bring a lot of water to drink. That really helps. I drank a lot the morning I went up. I was great. I ran out of water and I was just like, and you're in this funny state. And I sort of was thinking I'm in a funny state, but I wasn't thinking very hard about it. And I was just going along and. Okay, and so different wavelengths, radio telescope. This is in China, apparently. Okay, it's 10 minutes to 9. This is in China. And so they're these parabolic dishes. And so they reflect light and there's going to be something hanging above it. We've had Arecibo in Puerto Rico. It was someone discovered that it was a valley. It's a perfect valley. It was like someone said this could be a telescope. So they cleared the brush and they laid down. The original telescope was not all these shiny metal plates. It was just chicken wire on the ground. Because the chicken wire has spaces in it, right? But the radio waves are so long that to the radio waves, it looks like a flat sheet of metal. And so it reflected. And they eventually put in solid metal so they could get radio waves that were, shorter wavelengths. And so for different wavelengths, you have something different. And so interferometry with radio telescopes, you can link them together electronically. And so if you have two of them the same size, like this far apart, it's the same as having a bigger telescope with just two little openings in it. But you get more detail. The resolution goes way up when you do that. They haven't been able to do that yet with optical telescopes. I think they were thinking of doing it at the Keck, but I guess there were issues. They couldn't make it work or something. Nothing like that has happened as yet. This is Chile, and the sky is doing something funny up above it. And what is the sky doing here?
So light absorption over time.
No.
No, the photo is over time.
And why do you get, there's a center and there's rings.
Yeah, that's because when the Earth rotates,
Yeah, it's a time exposure. You're on a moving platform. They aimed at the North Star, which would be at the center of that circle. So that was pointing to the north. The telescopes weren't moved that night, or they'd blur out in the picture. And you got star trails. And it looks like, wow, it must have been very sensitive, pick up a lot of stars. Of course, I guess in the mountains there's no street lights and it must be phenomenal. But they're not that long. Each individual trail is not that long. So it might have been something like an hour exposure or something like that. X-rays, you can't focus X-rays, but someone came up with the idea that if we put these sheets of metal in there, then an X-ray coming in, if it hits it at this angle, it'll reflect off of it. And if we keep giving bunches of those things, then we can focus a lot of X-rays into one spot. And then we have it at that spot just for a bit, then we move it slightly, move it slightly, move it slightly, and we can build an image with many kind of dots. So rather clever. You can't focus X-rays though, but you can play games like this. And this is info on buying your own telescope. Start with binoculars. And you might want to get a tripod for the binoculars because you're standing looking at the sky, your hands are going to be shaking and, you know, you're not going to hold it that long, but if you have it mounted, you can just relax and look through it. It says magnification is not the important issue. You want to, you know, look at the amount of light, how portable is it, and how good are the optics? And check out these magazines and astronomy clubs. You can always, you know, and there's going to be blogs and things online, so you can, and people like to answer questions when they're posted. It's amazing that the information you can come up with. And looking, what's this? This is gravitational waves. Now, at the time, maybe these slides were made, I don't know. Gravitational waves had not been detected. But I think in the year 2015, they picked up gravitational waves. A neutron star, which we'll talk about much later, and a black hole, if those collide, or two neutron stars collide, the gravity around them is intense. And so when they come in and start colliding, they ripple the space around them, and these waves travel and long distances. And so I think there's one in Louisiana and one in the state of Washington. I think LIGO is initials for it, Laser Interferometer Gravitational Wave Observatory. So a whole new branch of astronomy. And probably there's going to be, you know, these things be put up in space where you can get much greater distances and link them by radio waves and maintain their distances and see what you pick up. And why do we put telescopes into space? They're closer to the stars, right? Well, you know, yeah, you are kind of closer by a wee bit, negligibly small distance. It's, and it's telling me here things to remember. The sun is like a grapefruit. Earth is a ballpoint pen. The nearest stars would have to be 4,000 kilometers away. And so one of the problems on the Earth is light pollution. People like to have lights on all the time. And at night, it used to be said that Earth, an alien coming in from Earth, couldn't see cities, couldn't see all sorts of things. They're always talking about the day side of Earth. The night side of Earth, everything's lit up. They're gonna see that something's down there. But light pollution, you got to have safe streets and all that. But even out in the countryside, people are crazy with light. And the LED lights are worse because they give off, because they're cheaper to run, they use less electricity, and they give off more light. People are using them more. So there's more light being produced into the sky. Turbulence. So ground-based telescope on the left and Hubble on the right. Which is the better image? Got to be the Hubble one, right?
Oh, no, I kind of like that Minecraft picture.
Yeah, that other one's kind of nice too. And the web pictures are even better than the Hubble if you've seen. Whoa.
Just looking at them, they're phenomenal.
Yeah, we have to hope that a hole got punched in one of those mirrors. They weren't expecting anything that size. They're expecting small. So nobody planned for this. You know, we have to hope that there's not a large population of things that size floating around out there, or somebody's head is going to roll after all that money spent putting something up that, and you can't go out and fix it.
Why don't you just get a ladder? I'm up there.
Yeah, there's the way. The atmosphere, this is a map showing what comes into the atmosphere. So visible light makes it to the surface. Some infrared to the right of it makes it down. Radio waves on the far right, they make it down. Now there's a lot of gaps. And to make up for the gaps, they do some infrared astronomy from a plane. There's this Sophia plane that's also the Vomit Comet, I think. They go up there and they open up the roof of the 747 or whatever it is, and they can measure infrared. They must have some way of taking into account the vibration of the plane. Because you want to aim a telescope at a point in the sky, and there is vibration in the plane. It's a machine that's running, right? So they must have good ways to damp that down. As you go to the left, ultraviolet doesn't make it through very much except longer wavelengths closer to visible light. They can shoot rockets up, and these rockets go up for a short bit and they take some measurements and pictures and stuff. Balloons are another way of going up there and measuring radiation that's coming in. And of course, satellites. And there's a bunch of satellites listed across the top here, some of which are no longer orbiting. I think Fermi and Swift are gone. I think all the rest are still up there. Chandra is an X-ray telescope. And so light pollution and turbulence. But basically the absorption by the atmosphere of the light alters what gets down there. And that's something that we got to do. And James Webb Telescope is going to launch in October 2018. It missed that deadline, didn't it? Missed a couple of them. And is this the Webb Telescope? Kind of. So it's got all these mirrors and they reflect toward the collector item, which is hiding behind or in front of a skyscraper building there. And it's got these blue sheets. What are those blue sheets for that it sits? 9 o'clock. 5 slides to go. I think we're out of here almost. What are the blue sheets for? You've seen the picture of the Webb telescope. And they're spaced apart.
Is that for the X-rays?
Nope. The Webb telescope has to be kept cold because it's going to measure infrared. And you don't want your telescope to be hot when you're trying to measure heat rays coming in. Because what are you measuring then? Your own heat most of the time, maybe. So it's got to be kept cold. These sheets are aimed toward the sun. And so the telescope mechanism is on the outward side of this array. And so when the sun shines on, it makes these sheets get hot, but they're hot there in space and there's space between them. So they get hot and then there's no way to cool them down in space. The only way you can cool something down, there's 3 ways you can lose heat: conduction, convection, and radiation. Convection is when you have, fluid, you blow air over something, it cools it, you blow on your coffee. Conduction is where 2 materials heat can transfer. You don't have conduction for a satellite in outer space. There's nothing for it to touch. There's no fluids going by it for convection. The only thing is radiation. You have to give it time to radiate. And so the strategy here seems to be to have these separate sheets. And the first sheet heats up and radiates in both directions. And some of it comes in onto the second sheet, which is not getting direct sunlight, and that gets warmed up, but not so much. And it radiates off, and so on, till you get down to the last one, and it's pretty minimal. And then the telescope mechanism is sitting there on top of that. And so it gets to maintain the chill of space, which is like 30 or 40 Kelvin. And where is it located? It's not in orbit around the Earth. Well, sort of it is. Yeah, the moon, it's on the, it's positioned, the moon is inside the orbit. It's 1.5 million miles out from Earth. Earth's shadow, I think, have we seen pictures of that, the umbra? Did we talk about that in the last couple of weeks? The umbra is like a cone or a triangular shadow drawn on paper. From Earth to the tip of the umbra is 1.4 million. So Webb is positioned at this point called L2, which is a special stable point in the gravity field of the moving bodies of the Earth and the sun. The gravity field is more complicated than you imagine. There's 5 L points, Lagrange points, and one is, let's see, L1 is between the Earth and the sun. It's 1 million miles out. We've got some observatories out there looking at the sun. and Earth moves and these points move with it. And they're sort of orbiting around that point. And there's a matching point out there at L2. And then on the far side of the sun is L3, which there's nothing there. Nobody's gone there to the other side of the sun, opposite from the Earth. And then if I think of the moon here and the Earth here, then on the moon's orbit, if I go 60 degrees along the orbit, I get the L4 and the L5 points. Things would be really stable if they're put there. I think there's some plan to put, is it the gateway that they're talking about for a stop-off point for people going to the moon or to Mars or whatever? Build a station there.
Gas station.
But yeah, you probably ferry things up from the moon, but you could store stuff and things could be delivered there and then picked up to go onward wherever. But those points are stable. Anything put there is going to stay there. Jupiter has, at its 60-degree points, has collections of asteroids. They're called the Trojans. And I think there's a spacecraft plan to go, Lisa, I think, but I could be wrong on the name. Is planned to go to the Trojans on one side and go around and see how different they are and whatever, and then cruise across and spend a little time on the other part. But anyway, they put Webb telescope out at the L2 point, and it's kind of orbiting around that point. There's some special, it doesn't take much fuel to keep it there, but they're keeping it there. And so it's a remarkable thing. You got to hope that it lasts. You know, the pictures, you just want to see these pictures. What can it see looking at Mars or Jupiter or Pluto? And anyhow, ground-based telescopes, adaptive optics will take an image like this and make it look like that. And looking at planet Neptune, without the adaptive optics, this is your picture, but with it, you got a lot of detail. It's not quite Hubble, but it sure is better than standard ground looking at it. Jupiter's moon Io, which is a volcanic moon, you can see where the volcanoes are with adaptive optics. But this is nowhere near the photographic quality that we have with it. And the moon would be a great observatory. Even radio, you talk about light pollution, there's radio noise pollution for the radio telescopes, and now you got, you know, all these constellations of GPS satellites up there, and they're just, you know, they're making a mess out of everything. So people have said, yeah, let's build on the far side of the moon. Then we won't have any radio noise. We've got craters, that'll be like Arecibo all over the place. Until people start living on the moon and they want their GPS satellites. And then, you know, you're back to where you started. Okay, so that kind of does it for tonight, I think. We did 2 chapters.
One more slideshow.
What?
One more slideshow.
I do have 2 more in there, but I'm going to have to load up. I get the rest. I've got 7 of them I put in a while back. I meant to get around to putting all the rest in. I guess I better do that this weekend. And I guess I better, mastering astronomy, I think I got to start making more assignments in there so I get the whole thing done. Didn't have time at the start, of course, to do it. Okay, let's see how I shut down here. Let's see, I guess I stopped the share. I'm going to stop the recording.